Okay, students, so now we are into lecture 8. We are into lecture 8, and you must be wondering that sir is saying I have only 2 reactions, there are 7 variables, Gibbs phase rule says you need 5 inputs. So if everything inputs outside, everything has been put in as inputs, then what is the use of doing metamorphic metrology? I mean, the number of variables is so big, the number of equations are so small, so majority of the variables cannot be established. Then what is the use of doing metamorphic metrology? PT conditions, we know that you can find pressure temperature condition, but here you're saying there are 5 variables and all can't be determined. Now how do you find pressure temperature conditions? I will let you know. It's a magnificent puzzle, this metamorphic metrology. It's brilliant always. I will show you how it is done. But first, let me now do the same things, but let me connect it to a metamorphic reaction. Let's do this first. Let's try to see how, when you see a reaction, a particular texture, and then you extend it to metamorphism, how it is really done. And this is what I will emphasize right now. Why? Say, for example, I have a pyroxene crystal. You know, a prismatic section of pyroxene with cleavage. And it is bordered by plagioclase. Bordered by plagioclase. But we also see that the grain of the pyroxene is not like this. It's sort of, it has an embayed borders. It doesn't have this euhedral shape. It's sort of xenoblastic. Not the euhedral shape, but it is more of an anhedral in nature. And at the contact of plagioclase and orthopyroxene, there are a mineral. There is a mineral, and this mineral has some inclusions within the mineral. There are inclusions. Let this mineral be garnet. And these black minerals here are quartz. So essentially what you can see here, this is called a corona texture, where the corona here is garnet and it contains intergrowths of quartz, which is not present outside. So essentially, we have some sort of a reaction. Orthopyroxene plus plagioclase is equal to garnet plus quartz. This is some sort of a reaction that may have happened. And since you know from common sense also, garnet is a very dense mineral. So if there is a dense mineral forming, it should be in the high pressure side in a pressure temperature diagram. And so orthopyroxene plus plagioclase in the low pressure and garnet plus quartz in the high pressure. So it's like this, vaguely. It's like this. And this is garnet plus quartz, and this is orthopyroxene plus plagioclase. I know it, so I'm telling you that it is a positive slope. This is very important texture. It has been shown in many, many granulite terrains and have been interpreted and reinterpreted and there are reinterpretations. There are a lot of things went on, and it's been reviewed again, revised again, and trying to see, no, does it really work like this, or there is something else. But it's a very famous texture. And you can see, if you're going from orthoperoxene to plagioclase, then either you're going this way, right, or you're going this way, or even this way. Now you see here, this is plus P, increase of pressure. This is minus T, cooling. This is plus P minus T, that means loading but cooling. And you have plus P plus T, that means you have loading and heating. This texture, orthoperoxene plus plagioclase and garnet plus quartz, the reaction lies like this. And from the pyroxene plus plagioclase field, if you go to the garnet plus quartz field, you can go different way. There are different paths by which you can do it. And it would be nice to know which path it has taken. That will take some time. But you can see, as we move along this path, or I move along this path, or I move along this path or this path, look at these points. Look at these points, these 4 points. Along these 4 points, or along the line, orthopyroxene plus plagioclase, garnet and quartz are in equilibrium. At these points on the path, say for example, when I go from here to the market, the Tikka shop falls to my left. So at a particular place, orthopyroxene plus plagioclase is equal to garnet plus quartz. When they are together, when they form an equilibrium, then we are somewhere on this reaction curve. And so what is important is this assemblage, orthopyroxene, plagioclase, garnet, quartz, is a very good estimate of pressure and temperature conditions. It gives us, it has been used world over, people have done it. The significance of it, the PT parts, let's not discuss this at the moment. We are still not there to realize the complications or the implications of this. But for the moment, we try and understand the assemblage orthopyroxene plus plagioclase is equal to garnet plus quartz. Now, important here is something else. You know, what is the system? What is the system? If you don't take a lot of complexity, if you don't bring on a lot of complexity, then the assemblage orthopyroxene, plagioclase, garnet and quartz. This can be very complex. You know, orthopyroxene is normally a solid solution of MgFe whole twice Si2O6. That's a normal, a very standard composition of pyroxene. Plagioclase, for example, is a mineral which is normally has NaCa, Al, Si, 4O8. Right? This has 2 components, NaAl, Si3O8 and CaAl2, Si2O8. This one here, the total of them is always 4. That is why I've written Al, Si. In albite, Al-Si ratio is 1:3. In anorthite, Al-Si ratio is 2:2. And you have all combinations of that. And if you take garnet here, Now, garnet normally is a more complex solid solution, but we take a simple garnet where you have CaMgFe whole thrice Al2Si3O12. This is a common garnet. It also, I remind you that it also consists of spessartine. Spessartine is manganese garnet. But if I leave that manganese part for you, and I show you a little bit, so if you take manganese here, then obviously pyroxene also contains manganese, because you can't form a manganese-bearing garnet from minerals which do not have manganese. It is impossible. You can't crystallize sodium chloride from water, where the water there is no sodium chloride. So it's like that. So here we have Ca3Al2Si3O12. The name of this component is grossular. Then you have Mg3Al2Si3O12. This phase is called pyro phase component. And you have Fe3Al2Si3O12. And this is almandine. So, and then of course, you have the great gentleman called quartz, SiO2. And here orthopyroxene has two components, Mg2Si2O6 and Fe2Si2O6. This is enstatite and this is ferrosilite. So the minerals are quite complex. If we add manganese, it adds some more complexity. So you have Mg2Si2O6, Fe2Si2O6, the two phase components of orthopyroxene. So orthopyroxene has two phase components. Plagioclase has two phase components. One is called albite, the other one is called adokite. Garnet has three phase components, according to what we have. And quartz has one phase component. These are the components. So the phase components are 2 + 2 4 + 3 7 + 1 8. So these are the number of phase components in the system that contains orthopyroxene, plagioclase, garnet, quartz. So phase, how many phases are there? Of course, it's 4. 1, 2, 3, 4 phases. Phase component is equal to 2 + 2 4 + 3 7 + 1 8. Now we come to the question of system component. System component. These are the three things that is first important. System component. What are the system components? You can well see that the system components will be FeO, MgO, Al2O3, SiO2, CaO. CaO, FeO, L. There is another one. Na2O for plagioclase. Na2O, CaO, FeO, MgO, Al2O3, SiO. So it's called NCF MASH. So this is NCFMAS. NCF mass. No no water. NCF mass. So the system components in this are 1, 2, 3, 4, 5, 6 system components. Have we got this right? Right. So we have system components, 4 phases, system component 6, phase components 8. Right? So let me erase it. Okay. So then, degree of freedom. F is equal to C minus P plus 2. Component is 6. Phase, number of phase is 4. plus 2, that's 4. So the degree of freedom is 4. Number of independent reactions, number of phases minus number of system components, and this is number of phase components is 8 minus number of system components is 6. So independent reactions are 2. Have I got this right? Number of phase components, 2 plus 2, 4, 4 plus 3, 7, plus 1, 8. Okay. And number of system component, NCFMAS reactions. So number of independent reactions is 2. What are the metamorphic variables? Now we come to the last question. We ask ourselves, what are the metamorphic variables? So once again, let's list it. Pressure, of course. Temperature, of course. Then, either XFE OPX or XMG OPX. This OR is important. So XFE OPX or XMG OPX. Then you have X albite or X anorthite. Sorry, this should be lowercase always, I told you. Anorthite. In plagioclase. Once again, the OR. Because they add up to 1. Here also, they add up to 1. And then, lastly, we have the garnet. Now, since quartz is a pure phase, so XSiO2 in quartz or activity of SiO2 in quartz is equal to 1, so it's quantified variable. So it's not a variable, it's quantified. And for the garnet, there are 3 components. So XFE in garnet plus XMG in garnet plus XCA in garnet is equal to 1, right? So here the variable will be XFE garnet, XMG garnet, or XCA garnet here. Or you could also do one thing. You could say XCA and X. You could bring in XCA here or XMG here. One of them is an independent. One of them is a dependent variable. Both of them. Out of the 3, 2 are unquantified. 1 is derived. So the number of variables therefore are 1, 2, 3, 4, 5 and 6. So the number of metamorphic variables, intensive metamorphic variables, 1, 2, 3, 4, 2 of 3, 2. So that should be 1, 2, 3, 4, 6 metamorphic variables. There are 6 metamorphic variables. Once again, you must be cursing me. There you go. There you go, sir. Once again, that's what we were saying. 6 metamorphic variables. You have 2 reactions. How can you find 4 input data? I mean, this is incredible. You could tell me. It's incredible. You are bringing so much to get so little. Is this a subject? Yes, it's a subject. Let me tell you. This, for example, anyone I will take, either this or this, it doesn't matter. These ones, these are easily determinable. Why? Downstairs, S122, there is a machine where if you put an electron beam on a particular mineral at a particular spot, 1 micron in size, the beam diameter is 1 micron. The area of influence is roughly about 2 to 3 microns. And when you put a beam on that, there's a huge electric current at around 20-25 kilovolts. What it does, it excites the surface. and it emits X-rays. So you have X-rays for iron, X-rays for magnesium, X-rays for calcium, whatever elements is there, it throws out the X-rays. And there is an analyzer which moves on a curve called a Roland circle. So it moves and at a particular wavelength. When you hit a beam straight on, the sodium wavelength, the iron wavelength, the magnesium wavelength, they have a particular angle at which it takes. These are called takeoff angles. So the spectrometer goes there, right at the place where you have sodium, it knows the angle, so it goes in there and detects it and analyzes it and gives you the values of XFEOPX if you're analyzing orthopyroxene. It gives you Ca and Na if you're analyzing plagioclase. It gives you all the elements, and it is done routinely in that lab. Right? So, these ones are determined. This you can find out in an equipment. This you can analyze in an equipment. You don't need to find them out using thermodynamics. You don't need. You need thermodynamics for using it. For finding the values, the instrument does it. It doesn't understand thermodynamics. So, all these variables, X variables that I'm talking about, they are determinable parameters. They can be found out from the equipment. So, if we do that, if you accept that, if you believe me that AB sir, what he's saying is right, and if you still don't believe, you have to go there and ask whoever is in the experiment, please show me how this is analyzed. And they will show you how it's analyzed. It's a very costly equipment, but it analyzes. So, this can be determined, this can be determined, this can be determined. All these intensive variables can be determined. So, if you know that, then you're left with pressure and temperature as the unknown parameters. You're left with pressure and temperature as the unknown parameters only. Have you understood? So when Gibbs phase rule says you have to give me data from outside, you go to that lab and analyze it, and you give him the data. How many? 1, 2, 3, and 4. It gives you 4 data. At the moment you do it with the Gibbs phase rule, 4 intensive variables are the inputs. You're back to this independent reaction 2. You're left with 2 variables. You find out pressure temperature condition from using the data. That is important. So when I was telling you those are unknowns and try to make a big story out of it, actually I was not telling you about this. In all other parameters, in all the previous examples, those X values are determined. The only values that are not determined are XH2O, XCO2, because the microprobe does not analyze. It only analyzes from beryllium to uranium. Does not analyze hydrogen. It cannot analyze hydrogen. And hydrogen is in the fluid. It analyzes minerals. It does not analyze fluids. Right? And another thing, it doesn't analyze carbon also, for one simple reason, that because this high electron beam, when it falls to the particular equipment called electron microprobe, then it is to make all rocks are electrically very poorly conductive. So what happens when you put on the beam and you don't allow the beam to flash out, so what it creates is it does not analyze it. So there is a buildup. So what happens? You coat it with carbon. So because carbon is a very good electrical conductivity, so once you hit the beam, the whole current is distributed. Have you understood? That is why carbon cannot be analyzed. But if you use gold coating on that, you can also analyze carbon. But carbon in what? Carbon in fluids. That fluid you don't know, it does not exist as a phase, you can't see it on the microscope. So you can't find and analyze. So those parameters are not found out. XH2, XCH4, XCO2, H2O2, these are not found out. What you find out is reference state elements. 90 till from uranium, from beryllium to uranium 92. all elements can be analyzed in electron microprobe, provided the detection limits are reasonably high. The concentrations are high. If the concentration is low, you cannot analyze. Then you require other ICP-MS or other instrument, which is also there in our department. So what is important here for the course of study is all these parameters are determinable. So Gibbs phase rule says 4, you get 4. The unknowns are pressure and temperature. These are the 4 unknowns. Have you understood? Now metamorphic petrology makes sense. But what are the reactions? Let's now look at the reactions. There are several reactions that can be written within this system, which is NCKF mass. N has gone. NC Now, what are the reactions? Let me write. Mg3 AO2 Si3 O12 plus. I will also tell you how to write reactions, but that comes at a later stage. Okay, let me do it from the outside. It will be easier. This is one reaction. This is one reaction. You can see here magnesium is 3, so you write 2 here. And you balance this magnesium with 3, so you have 6 magnesium. And now here you can see you have 2 into 2, 4 aluminium plus 2, 6 aluminium. So here you give 3 aluminium, so your aluminium is balanced. And this calcium balances this one. So magnesium, calcium and aluminium are balanced in this reaction till now. Now we have silicon. So again, like left hand side, right hand side. And left hand side, you see your silicon is 3 into 2, 6 silicon. On the left side, you have 6 silicon, so that's 12 silicon. On the right hand side, you have 6, 3. So you're down with 2, so it should be 3 SiO2. So that's 12 silicon atoms. So you're balanced your silicon atom as well. And then, for example, you can look at the oxygen values. 3 into 6 is 18 oxygen plus 3 into 8 is 24 oxygen. Let me write it. Left hand side and right hand side. Left hand side 3 into 6 18, 24, that takes it to 42. And on the right hand side, here you have 24 oxygen, 2 into 12, plus 12, and plus 6, 42. Your equation is balanced. Right? So that's important. So balanced reaction here. So out of the 2 independent reactions that you need, one reaction is this. Orthoperoxine plus an O-type component of plagioclase, N-cetite plus an O-type is equal to pyrope plus grossular. This is part of the solid solution of garnet, and that is quartz. This you can write, and you can write the iron end member reaction, which is 3Fe2 Si2O6 plus 3CaL2 Si2O8 is equal to 2Fe3 L2 Si3O12 plus Ca3 L2 Si3O12 plus 3SiO2. You see? Neither this can be derived from this or this can be derived from this. So both are independent reactions. Both are independent reactions. So now you have, as you said, all these can be determined from the instrument, and you're left with this pressure and temperature, and you can see here, if you solve this problem, if you solve this equation and this equation simultaneously, they should give you a function of pressure and temperature, because other variables are quantified. Other variables are determined in the laboratory through equivalence. So you can find out the pressure temperature condition at which, I won't go into the details of this because I think it's not necessary at the moment. We can find out the pressure temperature condition, equilibrium pressure temperature condition, where orthopyroxene and plagioclase and the garnet plus quartz the moment it formed. Right? But there are other reactions that are possible. Say, for example, if this reaction is A and this reaction is B, and I algebraically add it to remove, say, anorthite. You see, I write A minus B. A minus B. If I do this, then you will see this and this will cancel off. And also, this grossular and this grossular will cancel off. So, this and this will cancel off, and this will cancel off. So you will be left with 2 Mg2 Si2O6, I will just write it, plus Fe3 L2 Si3 O12 is equal to Fe2 Si2O6 plus Mg3 Al2 Si3 O12. And this is not balanced. So you see the 2 comes in here, the 3 comes in here, the 3 comes in here, and the 2 comes in here. Now you can see this and this are the same minerals. Mg2Si2O6, Fe2Si2O6. This is iron magnesium exchange between 2 orthopyroxenes. One is Mg2 between the 2 components of the orthopyroxene, and the counterbalancing is done by this one. So you have essentially 3 reactions possible. You can choose any 3. But any 2 of these 3 you can take, and you will be correct. So this is how you find out the pressure temperature condition at which garnet formed from orthopyroxene and plagioclase reaction. There is much more to it, but right now what we are discussing, I hope you understand it. Right? So what did we do? We took a texture of pyroxene plus plagioclase, giving you garnet plus quartz corona, and we took that assemblage and found out the phases, then we found out the phase components, then we found out the system components. This we found out only after we wrote the compositions of the minerals. Only after we wrote the compositions of the minerals, we were able to identify the different phase components and the different system components. Right. After that, we found out the Gibbs phase rule, and we saw the variance is 4. It says 4 input data, but we also saw number of independent reactions here is 2. So this means, and there are 6 metamorphic variables here: pressure, temperature, composition, 1, 2, 3, 4, and 2 of them. So if we give that data, then it leaves us only pressure and temperature to be determined, and we have A, B, C 3 reactions possible, out of which we can take any, theoretically, we can take any 2 of this and find out the pressure temperature condition of equilibrium between the pyroxene plagioclase and the garnet plus quartz. That is the important point. Now, if say for example, I say that I will leave this problem to you, I want you to solve that problem. What happens if our system, the same assemblage, you do it yourself, I won't tell you, you do it yourself. If the assemblage is Mn NCF mass, what happens to this? If there is Mn in addition, so you can see here, once again giving the clue, phases here are 4, it also remains 4 because we haven't added any phase as such. System components now, it was 1, 2, 3, 4, 5, 6, now you have 1 more, so you have 7, right? You have 7 now. Then the question comes, what are the phase components? Now, let's read. Orthopyroxene now will not have any more 2, it will be 3 now. Why 3? You can understand it. Plagioclase remains 2, because plagioclase does not take in Mn at all, but there is no Mn component of plagioclase. Garnet becomes 4, and quartz remains 1 because it's pure phase. So your phase component now becomes 3 plus 2, 5, plus 4, 9, plus 1, 10. So now you have 10 here, and not 8 as before. So now if we go to this one, degree of freedom, what will happen? This will become 7, right? 4 will remain as such. So you will have 7 plus 2, 9. 4 will change to 5. So metamorphic variables are 5 that you need for input. 5 unconstrained variables. Independent reactions. Now number of phase components here is 10. System components is 7. So this becomes 3. Now it's for you to find out what are the 3 independent reactions. This is for your practice. So first write down the phases, then write the phase components, then you write phases so many, phases components so many, system components so many. This is the degree of freedom, this is the number of independent reactions. Write down the independent reactions and you will be able to solve your problem. Remember, all compositional terms in the mineral phases can be determined by equipments. So when I say Gibbs phase rule says give this input, actually there are equipments from which you get this. By the way, I wanted to know from you please let me know in the Google Classroom whether you know how to calculate structural formula of minerals. Please let me know. Please remember and let me know whether you know how to calculate structural formula of minerals, including micas, hornblende, everything. Because it will become very necessary very soon. You please let me know in the Google Classroom. So this is how you go about the problem. Now you will have, instead of 2 reactions, you will have 3 reactions. Here, instead of 1, previously it was 1, 2, 3, 4. Now you will have 5 components, and those will be determined by the institute, by the equipment. You find out how it should be done. Remember, all compositions of minerals can be determined, but compositions of fluids cannot be determined. They are determined using thermodynamics, indirectly. So that's a completely different issue altogether. So now I have come to the end of it, of this integral part. Now I will move into a more of thermodynamics. So what I tried to tell you about from the beginning, if I recapitulate, I've talked to you about different systems. I talked to you about system surrounding interface. What are the exchanges that occur? Then we have talked about Gibbs-Duhem equation. We have talked about Gibbs phase rule. We have tried to find out what is the independent reactions. And then I told you about parameters that have to be input, output, how a particular mineral assembly is determined. Then we talked about fluid present, fluid absent situations. And now I think we can start having a quick test up within some time. And I hope that you will do well. But before that, we will have a mock test later next week, sometime in the weekend. So I will give you some dates. You try to give me dates which you all agree, and we can have it for 15-20 minutes so that you get conversant with the examination method, etc. I will tell you beforehand, you will not be graded. But after that, we will have class tests for about 30 marks. And I will set you a question. It's all open book questions, but you have to answer them. Obviously, they are not very easy to answer. Also, I think I stop here today. And again, I repeat that whatever I have talked till now, till video lecture 8, which is this one, they are of very fundamental importance to understanding metamorphic petrology. If you understand this, rest is a little not so difficult. But the concept of metamorphic petrology is difficult to build up. So you try to read and reread my video lectures and try to set your own problems in exercise notebooks, and you try to solve it. In case you don't try to solve it, then give the whole thing to me as to what your phase is, what your component, like I did to the board, and then you ask me, okay sir, I couldn't do it, where have I gone wrong? And I will try to help you out. Thank you.